So this is problem Q1 from assignment number 2, and we're told that a guitar string has a length L, a mass M, and it is attached between two stops that are a distance D apart, and D is not as long as L. So we're not given any numerical values here, just some variables to work with initially. And part A asks us to find an expression for tension of the string that it must be tightened to in order to produce a standing wave with a fundamental frequency F1. But because we're not given any numerical values, we're going to have to solve for this with the variables we're given. So first, I'm going to use the equation V equals the square root of tension of the string divided by mu, because it has this tension here that we're looking for. However, we don't have mu and we don't have V, but we can find mu because mu is equal to mass over length, which we have. And we're going to use length L here because mu is a property of the string, and we want to make sure that the entire string is accounted for here. And so now that we have mu, we can plug it into the equation up here and make it V equals the square root of tension of the string divided by mass divided by length. And that's fine, but we don't have velocity either, so we're going to have to do something about that. We're told that we're looking for the fundamental frequency, so let's look at the equation for frequency, and that is F equals M, which here means mode rather than a mass. That's going to be a number like 1, 2, 3 times velocity over 2 times the length. And we're looking for the fundamental frequencies, so we know that it's going to be F1 and M is going to be equal to 1. Still don't know velocity, divided by 2. And we're going to use D here instead of L for length because we're told that our string is caught between two stops and that it's longer than those two stops. So this is L and this is D. But the part of the string that we need to look at for the frequency is only going to be the part that's moving, and that's going to be the part that's in this length of D. The rest of it won't be affected because of these physical constraints put in by the guitar. So with that, we now have F1 equals 1 times velocity over 2D. And if you look at these two equations, we have this one for frequency and this one for velocity. You'll notice that they both have a velocity variable in them. So we can solve this equation for velocity, and that brings us F1 times 2D equals V. And then we have V equals square root of tension of the string divided by mass divided by length. And now we can set these two things equal to each other. So we now have F1 times 2D equals the square root of tension of the string over mass over length. And this is great because we know F1, we know D, we know L, we know M for mass. So we can just go ahead and solve for tension now. So what I'm going to do here is I'm going to square both sides. So we've got F1 squared, 2 squared is 4, I'm going to put that in front, D squared equals tension of the string divided by mass over length. That gets rid of our square root right there. And then I'm going to multiply each side by mass over length, and then that's going to give me 4 F1 squared D squared over L equals tension of the string. so that is it for part A here. And let's move on to part B. Okay, so part B now asks us to check our work, essentially. It asks us to use dimensional analysis to show that our derived expression for tension of the string, which we found to be tension of the string is equal to 4 distance squared, frequency squared, mass over length. And we are going to show that's correct by checking that the units on both sides of this work out. So tension is a force, and that means it's going to be measured in newtons, but 1 newton is also equal to 1 kilogram meter per second squared. So I'm going to put kilogram meter second squared here. 4 is unitless. We have d here, which will be in meters, and that's squared, so we're going to have meter squared there. We're going to have frequency here, which is in hertz, which can also be represented as inverse seconds. So we have seconds -2, so 2 inverse seconds there. We have a mass here, which could be in kilograms, divided by length, which would be in meters. This is going to cancel out. This is the same thing as saying seconds squared on the bottom. So if we clean this up, we'll see that this is kilogram meters per second squared on this side, and this is also kilogram meters per second squared. And that means that our expression for tension was correct. So part C is the last part, and it just asks us to draw the third standing wave. So because it's the third standing wave, we know that m is going to be equal to 3 here. Where I like to start is to find the nodes, and nodes occur at every x that is 1/2 times the wavelength. And we can easily find the wavelength using the wavelength equation, which says that wavelength equals 2L over m, m being mode here, not mass, and we have these variables, so I'm going to plug that in to give me that the wavelength is 2L over 3. And now we can say that nodes are going to occur at every 1/2 times the wavelength, 2 over 3 L, which is 1/3 L. However, it's actually going to be 1/3 D because we're trying to find the wave pattern here, and that's only going to be present in the part of the string that is between the 2 stops on the guitar and not the rest of its length. So I'm going to start by drawing our kind of guitar framework here. We're going to have forced nodes at these ends because of the physical constraints, so we can go ahead and put those in. And then we're going to have nodes every 1/3 of the distance, which is this total length here. So I'd say about there. That's a node. That's a node. And then we could put antinodes at amplitudes A, halfway between the nodes. And then we're just going to go ahead and trace out a sine wave between these points. And that is our third standing wave, and that concludes our problem.